Okay, so for FRK number 5, we have a pulley system with a block of mass M, which is 5 kilograms, at rest on a horizontal table that has no friction right here. And it is connected to a string that passes over a pulley of mass M over 20, which means it has 1/20th the mass of this mass and a radius of 10 centimeters. And the pulley is said to experience a frictional torque of 0.16 newtons times meters. And over the pulley, there is another mass right here, M over 2. That means it has half the mass of this mass, and it is hanging. Okay, so part A tells me to calculate the angular acceleration of the pulley. Alright, so first of all, they don't have the tensions labeled, so I'm gonna label them right now. So let's call this TO and let's call this TH. Alright, so I'm gonna apply Newton's second law to help me define those tensions, which will help me use torque to find my angular acceleration. Okay, so first of all, Newton's second law. Force is equal to mass times acceleration. So I'm gonna apply Newton's second law to two things, this one and then this object. So first I'm gonna apply it to the hanging mass first. So looking at the hanging mass, the forces that are acting on it is Fg and Th. Fg is the system's gonna move this way, so Fg is gonna be bigger. So Fg of mass m over 2, the opposing force is Th, and then that's equal to mass of the object, which is m over 2, times acceleration. Now my Fg of m over 2 is equal to m over 2 times g. So I'm going to plug that in. Now I want to define Th, so I'm going to isolate for it. I'm going to add Th to the side and subtract m over 2a to the side. So essentially Th is going to be equal to m over 2g minus m over 2a. So that's Th defined in these terms. Now for the other object. Now the only force acting on this object is tension right here, TO. So apply Newton's second law to this object. We have TO is equal to the mass of the object, which is just m, times the acceleration. And it looks like it's already defined. Okay, so now since we have our tensions defined, we're going to use torque to help us find our angular acceleration. So I know that the total torque is equal to the total force that's perpendicular to the molar arm times the molar arm. I also know that torque is equal to the moment of inertia of the pulley times its angular acceleration. And this is what we're trying to find. Now, for this side, first of all, I'm going to define my moment of inertia for the pulley. So I pulley is equal to 1 over 2, that's the coefficient, times the mass of the pulley, which is m over 20, times r squared. This reduces down to 1 over 40 mr squared. And so I'm going to plug that in right now, along with my total force that's perpendicular to r. So first of all, I'm going to plug in the total forces. So I have TH right here and TO. TH and TO are opposing each other, and TH is going to be bigger because the system's moving this way. So I have TH and minus TO and times R. But I can't forget that I have a frictional torque. So I'm going to add it in there, or subtract it in there right now. So minus torque of friction. And that's equal to, so plugging in my moment of inertia for the pulley, 1 over 40, m times r squared, then times angular acceleration. Alright, so now I'm gonna define, or I'm gonna plug in my what I defined for my tensions in the previous parts. So this and this for TH and TL. So I have m over 2 g minus m over 2a for my TH, then minus ma for TL, then times r, minus torque of friction is equal to 1 over 40. Basically everything stays the same. Then times angular acceleration. Now I know that, wait, I'm trying to find angular acceleration. Okay, so I know that my a right here is equal to angular acceleration times r, and so now I'm gonna substitute that in right now. But I'm also going to distribute the r as well, so I'm doing two things in one step. So that's m over 2 times g, and then distribute the r, so m over 2 times g times r, minus m over 2 times a. I'm going to substitute this in, so times alpha times r, and then there's another r right here, so r squared. Same goes for this one, so m times a is alpha times r, and then another r distributed, so r squared, minus torque of friction, and that's equal to, this side stays the same, 1 over 40 mr squared, and then alpha times alpha. Alright, so at this point I'm going to combine all like terms, and it looks like that these two terms, these two are alike with this term over here, so I'm going to add those two terms over here. So this side is going to be left with m over 2 times g times r, basically this term, minus torque of friction, and that's equal to, so I have to get a common denominator, right? So if I add these two over, it's going to be 1 over 40 plus 1 over 2 plus 1. Now to get common denominator, I times this by 20 over 20, so 1 over 40 plus 20 over 40, times this by 40, so 40 over 4, 40 over 4, and then times it by 40 over 40, so I get that. This ends up giving me 61 over 40. So this side is going to be 61 over 40 mr squared times alpha. Okay, I want to solve for alpha, so I'm going to times this side by the reciprocal of this, or basically just divide this whole thing over to this side. Okay, so alpha ends up being, so this whole thing up here, m over 2 g r minus torque of friction over 61 over 40 mr squared. So that is my equation for alpha. Now I'm plugging my numbers. So I got mass, m is 5 kilograms, g is 9.8 meters per second squared, r is 10 centimeters. Now, so r is 10 centimeters. I'm gonna convert it to meters. 10 centimeters to meters is 0.1 meter. So it's gonna be 0.1 meter minus torque of friction. Torque of friction is 0.16 newtons times meters, and it's over 61 over 40 times mass. M is 5 kilograms, and R is 0.1 meter square. Okay, plugging this all in the calculator, my alpha turns out to be 30.033 rads per second square. So this is the angular acceleration of the pulley. Alright, now part B wants me to calculate the speed VH of the hanging block after it has descended a distance of D. Alright, so first of all, I'm going to convert my I'm going to find my acceleration of the block first. Now I know that the acceleration of the hanging block is equal to the angular acceleration of the pulley times its radius, R. So that's 30.033 rads per second squared. Basically this times R, 0.1 meter. So my acceleration of the hanging mass is 3.003 meters per second squared. Okay, now that I have this, I'm going to use a kinematic equation to help me find the speed VH after it has descended the distance of D. Okay, so first of all, D is 2 meters, by the way, so that will be essential to know. So I have the kinematic equation I am going to use is VF squared minus VI squared is equal to 2 times acceleration times the distance traveled. So in this case, VF is VH that we're trying to find, squared. VI, initially the system's not moving, so it cancels out to 0. So 2 times acceleration is right here, 3.003 meters per second squared, and distance is 2 meters. 2 meters. So if I want to solve for VH, I square root this side. So VH is equal to the square root of 2 times 3.003 times 2 meters. Plug this in the calculator, I get 3.466 meters per second. And that is VH, or the speed that the speed of the hanging block after it has descended a distance of 2 meters. Alright, now part C wants me to calculate the tension TH connected to the hanging mass. So the tension of this part of the string right here. So this should be easy since I have my acceleration. I've already defined TH somewhere up here. So let's see. So I defined TH to be equal to this, m over 2g minus m over 2a. So as a reminder, TH is equal to m over 2g minus m over 2a. I have all these numbers, so I just have to plug them in. M is 5 kilograms. G is 9.8 meters per second squared. Minus m is 5 kilograms once again. Minus over 2 times A. A is 3.003 meters per second squared, right here. Plug this all into the calculator, you get 16.992, and my units is newtons. Alright, now we are given this new scenario now. Now it says that the block and the pulley is replaced with a uniform rope of length L and a mass of M, with one end of the rope hanging slightly over the edge on a frictionless table. The rope is released from rest, and at some time later, there is a length Y of the rope hanging over the edge. Express your answer to part D, E, and F in terms of Y, L, and M and fundamental constants. So part D tells me to determine an expression for the force of gravity on the hanging part of the rope as a function of Y. Okay, so part D. So FG hanging, FG hanging is what I'm trying to find, and I know that FG is equal to mass times gravity. Now this mass right here is the mass that is hanging, and now I have to define it in terms of the mass of the entire rope instead of just the mass of the hanging part. So I'm gonna write it down what it means. So M here represents the mass of portion of rope that is hanging, and I know that M prime, I'm calling this M prime, is equal to the mass of the total thing, the mass of the entire rope, times the fraction of this fraction, which is the amount, the length of the rope that is hanging over the total length of the rope. So that is what the mass of the portion of rope that's hanging is equal to in terms of M and Y. Okay, so now I'm gonna plug that in. So FG is hanging is equal to M times Y times G over L. And that looks like that is my equation. I've defined FG in terms of Y, so, and then other constants, so that looks like that is what they're looking for. Okay, so this is my answer to part D. Now part E. Part C says to derive an expression for work done by gravity on a rope as a function of Y, assuming Y is initially 0. Well, this is quite easy. Work is equal to force times distance. Now the force applied is gravity, so Fg hanging, and the distance is gonna be Y. Fg hanging we defined up here, so we just have to plug them in. Mgy oops, this is myg over L times Y. I can combine this to be equal to mgy squared over L, and this is equal to my work done right here. So that is my equation for the work done in terms of these variables. Now part F says to derive an expression for speed Vr of the rope as a function of Y. Okay, so I can use work once again to help me do this, because I know that work is equal to a change in kinetic energy, and the kinetic energy is KEF minus KEI. Since KEI is 0, since the system's not moving initially, that means my work is going to be equal to 1/2 m times Vr squared. Now this gives me a relationship between work and Vr, which is what I'm trying to find. So this is what I have. Alright, now work I've defined up here, so I'm going to plug it in right now. So mgy squared over L is work up here, and that's equal to 1/2 m times Vr squared. The masses cancel out. I want to isolate for Vr, so I times 2 and square root everything. So Vr is going to be equal to, let's see, times 2, g times 2 times g times y squared, and then divide by L, and then square root everything. that is my equation for VER, and we're done.